Forming solutions. So solutions are formed because a solute dissolves in a solvent. There are several steps that are required for this to happen. First, the coulombic attractions within the solute and the solvent are weakened so that the molecules in both the solvent and the solute are no longer bound together. Once they're separated or weakened, new coulombic attractions can form between the molecules of the solvent and the solute, combining them to one another. In order to weaken the coulombic attractions initially, energy, or more specifically enthalpy, must be added to the system. Then, as new attractions are formed, enthalpy is released. As an example, let's look at the formation of an aqueous solution of glucose. So we have glucose in solid form, and then we're dissolving it, so it ends up aqueous or dissolved in water. So what has to happen? Well, first, the intermolecular forces between the glucose molecules must weaken. That requires an input of enthalpy or a positive enthalpy change. Also, the intermolecular forces between the water molecules must weaken. That's also a positive enthalpy change. And then new coulombic attractions form between the solute and solvent. And when that happens, you have an overall negative change in enthalpy as energy or enthalpy is released. Now, the sum of these three changes would be the net change in enthalpy for the solution. We specifically here, because we're talking about dissolving, we call that the heat of solution, and it's specific to particular solute-solvent combinations. So sometimes those will have an overall net positive enthalpy change, and other times the net overall change will be negative. The heat of solution, which we'll call delta H, will vary depending on the affinity of the solute for the solvent. Reactions with a negative value of delta H occur spontaneously, and reactions with a positive delta H do not occur spontaneously and require additional energy be added in order for the reaction or the dissolution to occur. For example, ethanol has a very different heat of solution when dissolved in water because it's polar versus when it's dissolved in hexane because it is a nonpolar solvent. When ethanol is dissolved in water, the overall heat of solution, delta H, is negative 10.7 kilojoules per mole. So remember that it requires enthalpy to break apart the ethanol. It requires enthalpy to break apart the water. But then remember that when the coulombic attractions form between the ethanol and the water, in this case, we get the formation of these hydrogen bonds between the water molecules and the ethanol molecules, and that's a very, very big negative enthalpy or release of energy, and so the net delta H is overall negative. On the other hand, if I dissolve ethanol in hexane, I get this positive enthalpy, and that's because, again, ethanol is polar and hexane is nonpolar. So when the two parts, solute and solvent, decrease their coulombic attraction for one another, we still have these positive inputs of energy. But the polar solute does not have an affinity for the nonpolar solvent, so we don't get that negative release of energy required to offset or weaken the solute-solute and solvent-solvent attractions. So the overall delta H for ethanol dissolved in hexane is positive. An ideal solution is one for which the heat of solution is 0. An ideal solution is most likely to occur when the solute and solvent are extremely similar in both molecular structure and polarity. So for example, this methanol and ethanol solute-solvent combination are nearly identical. The difference here is just a single CH group. And in the next example, we just have a difference in the number of carbons. And in the next example, difference in the number of carbons and hydrogens, but very close to one another. So why is the heat of solution for these types of solutions 0? Because the heat of solution comes again from those Coulombic attractions of the solute and solvent particles separating and then forming new Coulombic attractions. So the solute molecules and solvent molecules have Coulombic attractions that are almost the same as those attractions between the solute and the solvent because the two are so similar. The heat of solution can be calculated by monitoring the temperature change when the solute and solvent are mixed. The heat of solution can be found using the equation delta H equals mc delta T, where m is the mass, c is the specific heat, and delta T is the change in temperature. For example, when 5.3 grams of NH4Cl are dissolved in 100 grams of water at 22 degrees Celsius, the temperature of the solution drops to 18.7 degrees Celsius. Assuming the specific heat of the solution is 4.2 joules per gram degree Celsius, what is the heat of solution? Okay, so the energy lost by the solution, or delta H, is M, so 5.3 grams of NH4Cl plus 100 grams of water is 105.3 grams, times C, the specific heat of the solution, 4.2 joules per gram degree Celsius, times delta T. So if we start at 22 degrees and the temperature drops to 18.7 degrees, the change in temperature is 3.3 degrees Celsius, which is an energy loss of 1,460 joules. In kilojoules per mole, that would be 1.460 kilojoules per 1 mole, per 0.1 mole of NH4Cl. And that just comes from taking this 5.3 grams and converting it to moles using the molar mass from the periodic table. And we get 14.6 kilojoules per mole. Ionic solutes dissociate into ions in aqueous solvent. Okay, so the example here is the dissolution of the ionic solute NaCl salt in water, H2O. What happens is in solution, the sodium chloride solid becomes ions of sodium and ions of chlorine in aqueous solution or dissolved by water. What happens is each ion becomes solvated or surrounded by water molecules. So remember that for a water molecule, the oxygen is partially negative due to the polarity of the molecule, and that partial negative is attracted to this big positive, sodium, solvating it. Covalent or molecular solutes do not dissociate into ions. So the example here is the dissolution of glucose, C6H12O6 in water. So again, we start out with solid glucose that is dissolved in water, aqueous. So what happens? Well, the glucose molecule, the individual glucose molecule doesn't separate or ionize, but the entire glucose molecule becomes solvated or surrounded by water molecules. And again, you can see the partially positive oxygen side of this water molecule is the partially negative of that oxygen in the water molecule is lining up near the more positive side of that OH group where the hydrogen is. And the opposite happens here, right? Where this hydrogen and oxygen orient themselves. And here it's the hydrogen and oxygen. Okay, so the water molecules orient themselves appropriately. to solvate the covalent glucose molecule. Electrolytes are solutions that have mobile ions that have been released by the solvation process. Electrolytes are excellent conductors of electricity. So you think of like a Gatorade or any other sort of sports drink that's full of electrolytes. If you read the ingredients there's often a lot of sodium, potassium, and other ions that act as electrolytes. So soluble ionic compounds like sodium chloride, potassium chloride, and strong acids, so remember those 6 strong acids, make excellent electrolytes. Covalent, and that's because they dissociate into ions completely, right? Completely into positives and negatives. Covalent molecular materials make poor electrolytes because they do not dissociate into ions. So the sugar example that we just saw is a good example. The more ions that are produced in solution, the stronger the electrolyte. So let's say we have equimolar solutions of sodium chloride and magnesium chloride. I've shown the dissolution of both, or the dissolving of both in aqueous solution. NaCl becomes Na plus and Cl minus. MgCl2 is Mg2 plus ions and 2 Cl1 minus ions in solution. So which compound is the stronger electrolyte? So again, more ions is a stronger electrolyte. Okay. This sodium and chloride here is a total of 2 ions. This magnesium ion and the 2 chloride ions is a total of 3 ions in solution. So the magnesium chloride will always dissolve more ions in the solution. And so it is the stronger electrolyte. Now let's compare equimolar solutions of HF and HBr. So we have HF dissociates into H plus and F minus, and the same is true for HBr, H plus and Br minus. Okay. So remember that HBr is a strong acid. So it's going to exist entirely as ions, H plus and Br minus. HF is not a strong acid, so actually we should probably draw this as a 2-directional reversible reaction where some of the acid will exist as ions, H plus and F minus, and some will exist as HF, not as ions. Okay, and so because the HBr is the strong acid, which completely fully dissociates, it'll have more ions in the solution because it'll have only ions in the solution and therefore be the stronger electrolyte.